My name is Paul Robinson. I'm Research Director at Southwest Research and Information Center, a nonprofit research organization based in Albuquerque, New Mexico in the U.S. I've worked there for 42 years, and during that time also taught environmental assessment methods at the University of New Mexico. Uranium is found in most rock around the world. It's naturally occurring, and the average concentration is about 2 parts per million in most rock. Natural uranium is made up of 3 different forms of uranium or isotopes. They're identified by their atomic number, by the amount of materials in the nucleus of the atom. So there's uranium-234, uranium-235, and uranium-238. The uranium-238 is 99.3% of the natural uranium. The U-235 is 0.7% of natural uranium, and the 234 is less than 0.1%. The uranium can be identified through the radioactive emissions, and so prospecting for it can be done through that radiation detection as well as conventional mineral exploration methods. Once the uranium's identified, then there's several different mining methods. There's open pit mining, where the ground covering the uranium is removed, the uranium ore is taken out and processed. If the deposit is too deep for open pit mining, then shaft mining will be used, where there's a vertical elevator constructed, a mine shaft, horizontal tunnels into the deposit, and the uranium ore extracted and carried up the shaft. A third method is in situ mining, a solution mining method where a liquid is injected into the ground in a borehole, and the liquid is extracted near that borehole from an extraction well. The extraction well is pumped harder than the injection pressure, so the solution is drawn to that extraction well where the solution is removed. That solution is designed to extract uranium from the rock, and so that solution is processed, the uranium removed, and most of the solution recycled and reused for continued solution mining. Uranium has 2 primary uses, both based on the radioactivity characteristics. The 235 is the uranium atom that can be split to generate fission, the kind of reaction that releases energy, and that fission energy is used in the power generation and is the fundamental source of the energy in a nuclear bomb. Currently, the largest producer of uranium is Kazakhstan. Canada, Australia, Niger, Uzbekistan, South Africa, those are among the top 10. The U.S. has a lot of uranium, but it's very expensive to produce compared to these other countries, so the U.S. is in the bottom half of the top 10. Uranium that is natural needs to be concentrated as a first step in the uranium beneficiation and enrichment process. And so the ore that's taken out of the underground mines, the open pit mines, it's run through a chemical processing mill. The ore is crushed to sand grain size, run through a series of vats and tanks with leaching chemicals, and the uranium separated from the chemicals and the ore. The chemicals in the ore become waste, and the uranium is recovered as a uranium oxide that's called yellow cake. The solution mining produces a solution that needs to have the uranium in it concentrated to the 90% of natural uranium, similar to the yellow cake. Each of these different stages of uranium mining, milling, conversion, enrichment, fuel fabrication, and then use in power stations all produce very large volumes of waste. The ore, once it gets to the mill, creates 999 times as much waste as product. The mill waste contains 85% of the radioactivity of the ore because uranium, when it occurs naturally, is unstable, it's radioactive and decays, meaning it breaks apart. The uranium-238, the dominant part, the 99%, breaks apart, decays according to a well-known and well-studied series of decays. So the decay products include thorium-230, radium-226, radon-222, and other decay products. And each of those decay products are more radioactive than the natural uranium and have well-identified health effects if people are exposed to them. The ore typically includes other heavy metals such as lead, nickel, selenium, arsenic, cadmium, different mix of heavy metals depending on the deposit. And those are hazardous constituents, and those are typically left in the tailings. There also are wastes produced during the mining stage. During an open pit mining activity, there's overburden and waste rock produced that's generally 3 to 5 times as much waste rock as there is ore. And so there's 1 volume of ore, 3 volumes, 3 times as much mine waste. And once the ore is processed, then you have the 1 part yellow cake and the 999 parts mill tailings. So there's vastly more mine and mill waste than there is uranium produced, and only the uranium is shipped off-site. The mine waste stays next to the mine, the mill waste stays next to the mills. So the places where those are located, whether they're communities, whether they're water sources, agricultural fields, grazing lands, those communities face the long-term risk from the mine and mill waste releases. Only the concentrated uranium is removed. During the first 50 years of uranium mining, there was no reclamation of any mines or any mills. And so there's a backlog of thousands of mines and hundreds of mills that have been a focus of investigations, and many have begun to be reclaimed since the mid-70s, when the low-level radiation and chemical hazards were identified as having caused health effects among miners and nearby populations. Here in Colorado, 4,000 homes and 16 schools were built with concrete using uranium mill tailings. There were schools, homes, and other buildings in about 20 other US towns. In East Germany, which was the large source of uranium for the Soviet Union, there was also extensive use of uranium in road and uranium mill tailings, which had a radioactive content in road and housing construction, and also in the former Soviet Union. In a town called Balai in Chita region, most of the workers, the poor people, had wooden homes. The mine managers and the political commissars, they had concrete homes, a little fancier, made with uranium mill tailings. And so this exposure of non-worker populations by use of tailings in construction was a very powerful motivation for beginning to address the reclamation of the mill tailing sites and the deconstruction of those homes, replacement of the yards around them, replacement of the concrete. So these exposures were identified in the 1960s and 1970s. The Uranium Mill Tailing Radiation Control Act in the US was passed in 1978. That was the first time uranium mill reclamation and uranium mill tailings reclamation was required, and that included the demolition of these homes, compensation of people who'd been living in these world. In situ mining currently occurs in Russia, in Kazakhstan, Uzbekistan. And the in situ method requires that the uranium be in a water-bearing layer, so that when you're injecting the leaching solution, it's mixing with liquid that's already there, rather than it being in a dry ore zone. And so only where the ore occurs in the water table underground is it possible. In order to carefully manage these injection and production wells, the design requires confining layers above and below the ore zone so that the injected fluid is able to be controlled rather than flowing out of the zone through the overlying or underlying systems. And the drilling techniques require a series of boreholes that are spaced 20 or 30 meters apart over the whole extent of the ore body. So there's substantial surface disturbance, piping, roads, wiring, because the mining is done by pumps rather than workers. Very few employees in an in situ mine, just the computer operators monitoring the pressure in the injection and extraction. So it's not clean, it's just a different set of problems, but a much cheaper method. So companies like to find opportunities to use the in situ method. Well, the various methods, the underground mining and in situ, have been evolving over the last 50 years. So the methods are improving. To me, having very careful monitoring is very important, so there's a very thorough understanding of what releases are occurring, if any. A successful monitoring system and a successful operation would include monitoring that shows there were no releases. One of the important best practices is to ensure that any operation has a fully funded, guaranteed decommissioning plan, so that the decommissioning plan is fully detailed and the cost of the operation of that decommissioning plan is put into a bank or put into an insurance policy, so that if the company abandons the site, goes bankrupt, there's enough money to do the job without the company there. That bond serves as an incentive for the company to do a good job, because the restoration work is going to be cheaper if the company uses its own equipment than the agency that has to do the restoration after the company leaves has to buy its own. If a company goes bankrupt, you can't use their equipment. It's owned by the creditors, so the restoration, decommissioning requires an estimate of third-party costs that include the redesign, include insurance, include monitoring and maintenance, and include the income for those companies. So just having the restoration methods is not the full cost of decommissioning. I think that there's lots of risks associated with uranium mining, because the materials, the uranium itself and the uranium decay series and heavy metals associated with it, and the sulfuric acid used in the underground leaching or milling process, all are hazardous chemicals. And so managing them as hazards to prevent releases is the only way to prevent health risk. So they're not safe materials. They're not inherently safe in any way. And so having a mining and monitoring method that respects those risks and tries to minimize or eliminate them is a much more viable approach than trusting someone to do a good job without them having to prove it during the operation.